Welcome to A Level and AP Physics. In today's lesson, we will discuss past paper questions from March 2024, Paper 4, Variant 2. As always, we will discuss these questions in detail so you can improve your conceptual understanding of physics and also you can have better understanding of these exam questions. Let's study together, let's improve together. Question 8, Part A says, state what is meant by the binding energy of a nucleus. Binding energy of a nucleus is the minimum amount of energy needed to separate the nucleons of a nucleus to infinity. It simply means that we can imagine we have this nucleus. This nucleus has two protons and it has two neutrons. The amount of work we need to separate these nucleons to infinity means they are far away from each other. So we can say we have neutron here, we have neutron here. So the amount of work done by the external agent, the minimum amount of work done, that is the binding energy of this nucleus. Now let me show you how you can write down the answer. In the answer you have to mention these points. You have to say that minimum amount of energy required to separate the nucleons of a nucleus to infinity. If you have written this, you will get 2 marks. Part B says a nucleus of uranium-235 absorbs a neutron and becomes unstable. It then undergoes a fission reaction. One possible reaction is shown here. Determine the number of neutrons produced in this fission reaction. So simply we need to understand we have mass number here, we have mass number here, we have mass number here, so we have mass number here. And for neutron, we need to understand neutron has no charge, but its mass number is 1. So simply we can say this is 0, this one is 1. Now if you get mass number, we on left side we have 235 plus 1. This has to be equal to 142 plus 90 plus, we can simply say something has to be here. So this is representing the number of neutrons, and this is possible. Here we will have 236, so here we have 142 plus 90, so we have 132, so this one has to be 4. So 4 neutrons are produced. So simply we can say here 4 neutrons are produced. Second part says data for the binding energies per nucleon for this fission reaction are given in table 8.1. Calculate the energy released in mega electron volts from the fission of one nucleus of uranium-235. Uranium-235. So we have to look at this equation. So in this case we have uranium, so this is a nucleus, and this is individual particle. Individual particles like neutrons, they do not have binding energy attached with them because they are individual particle already. They are not in the nucleus, so they do not have binding energy. So we have daughter product here, we have daughter product here. These are also individual neutrons, so no binding energy. So I can say no binding energy because they are individual particles, they are not in the nucleus. So you have to be very clear about this. So how we can calculate energy released now if binding energy per nucleon is given to us. So in this case, one thing also you need to understand, in this reaction, if we go this way, binding energy per nucleon, so you have to be very clear. So this point is very important. Listen carefully. Binding energy per nucleon is increasing, but mass is decreasing. So in this case, mass is decreasing. We can also say mass per nucleon is decreasing. Very important point. Mass per nucleon, this decreases. So if the mass is given to us, mass of each nucleus is given to us, so we can calculate energy released by simply using mass defect. Energy released. So energy released we can simply calculate by mass defect, means delta M we can calculate and we can multiply with c square, so we can find out energy released. That in this case mass defect we cannot calculate. We have binding energy per nucleon, so how we can calculate energy released? This question is tricky question and it is very common in recent years, so you have to be very clear how to answer this type of problems. Energy released. So energy released in this case will be equal to total binding energy. So this is the concept. Total binding energy of products, very important one, of products minus total binding energy of parent nuclei. So we can say of parent nucleus. So this is the main concept. Now simply we need to plug in values and we can find the answer. So how we can calculate total binding energy of the product? So here we have mass number 142. So we have 142 and binding energy per nucleon is given. 142 is the number of nucleons and binding energy per nucleon is given to us, that is 8.37. So we multiply with 8.37 plus, so plus we have this nucleus, nucleon number is 90 and binding energy per nucleon is 8.72. So we can write on here 8.72 and minus negative here we have this nucleus, number of nucleons we have 235. So we can say 235 and binding energy per nucleon is given, that is 7.59. So that's all. This is how you need to do. Now if we do simple mathematics, we will get answer in this case 190 mega electron volts. So this is the final answer. So individual nucleon means individual particle, not individual nucleon. There are no individual nucleon. Nucleon means particles in the nucleus. So individual particles, they do not have binding energy. And in any reaction, mass per nucleon decreases, means the mass per nucleon of products is lower, or you can say the total mass of total products. But when you are using mass defect, you have to consider the mass of individual particle as well, because we calculate the difference between the total mass of the products and total mass of parent nuclei. So these points you have to be clear how to answer. And in every reaction, binding energy per nucleon of products is greater than binding energy per nucleon of parent nucleus. So if these points are clear to you, you can handle these questions with confidence. Third part says the isotope xenon 142 is unstable. The isotope xenon 132 is stable. Suggest a reason why xenon 142 is unstable. As these are isotope of the same element, it means that they have same number of protons. As this one has a higher mass number, it means this one has more neutrons. So as the ratio between neutron to proton increase, isotopes become more unstable. So simply we can say the ratio between neutron and proton is higher for xenon 142. So that's reason 142 is unstable. So for the answer of this question, simply you can say its neutron to proton ratio is too high. So this is unstable. Part 4 says xenon 142 decays into the isotope cesium 142. A sample initially contains only nuclei of xenon 142. After time equal to 6.0 seconds, the ratio between the number of decayed nuclei of xenon 142 and number of undecayed nuclei of xenon 142 is equal to 31. Calculate the half-life of xenon 142. Show your working. This question is straightforward, and also this question is very tricky if your basic concepts are not clear to you. First of all, when some student, they will look at this question, they will just understand, they will interpret this one like this, that n over n naught, this is equal to 31, and then they will use the formula, that n is equal to n naught e to the power of minus lambda t, and they will try to figure out value of half-life. Lambda in this case is decay constant. They have this misconception because actually they don't understand what this n is representing. This n is a function of time actually. So this gives us remaining nuclei at any given time, or we can say this is giving us undecayed nuclei. Number of undecayed nuclei at given time. given time. Given time t. T is the given time. And what this n is representing, this is initial number of nuclei, means in the sample, total number of nuclei in the sample. So we can say initial number of nuclei. Initial number of nuclei. Now you have understanding of this formula, so you will not use n over n naught is equal to 31, because that is wrong, because this is giving number of undecayed nuclei. This is number of total nuclei, and that is not here, so we need number of decayed nuclei. So you will not use this one. Now your concept is clear. Now we will proceed to find the answer of this question. So we can write on here, first of all, number of decayed nuclei. So if you have the total number of nuclei n naught, and remaining nuclei we have n, so this will be decayed nuclei. Undecayed nuclei we have already said this is n, and this is equal to 31. I hope this makes sense. Now we can simplify this one, so we can say in this case n naught minus n, this will be equal to 31 times n. So from here we can say n naught, for example, this minus n will be positive here, so we will get 31 plus 1, it means this will be equal to 32n. So now we got here n over, so here we got n naught by n, this is equal to 32, or we can say n over n naught, this is equal to 1 over 32. So this is here. Now simply you have to use this formula. So let me write down here. So now we have n over n naught, so here we have n over n naught, that is equal to 1 over 32, and this is equal to e to the power of minus lambda t. Lambda is a decay constant. We need to calculate half-life, so the lambda will be equal to ln 2 ln 2 divided by half-life t1 by 2. So this is how you can calculate decay constant. So now we can simply say we have 1 over 32. So here we have 1 over 32, means this one we replace with this, and this is equal to e to the power of, here we have ln 2, this is divided by t half-life, so t1 by 2 multiply with t, so this is the time given 6 seconds, so here we have negative. Now if we take ln on both sides, ln here means ln here, so let me write on here, we have ln, here we have 132, and if we take ln here, so you can rewrite this one, so I'll just write down directly. If you take ln, what you will get here, if you take ln, you will get, this is minus, ln is 1, so that will be cancelled, so we will have ln 2 and multiply by 6, so we can say this will be minus 6 ln 2 divided by t half-life t1 by 2. So this side what we will get, minus we will get, this is ln 32, because this is 32 here, so the power is minus 1, so minus 1 will come in front of ln, so we will say minus ln 32, this is equal to minus 6 ln 2, this is divided by t1 by 2, means the half-life, so negative negative will be cancelled, so these two will be cancelled. Now we can write on here, so we have t half-life, so we can say t1 by 2, this will be equal to 6, and here we will have ln 2 divided by ln 32, so here ln 32, so we have 6, so t32, so this is divided, and if you solve this one, so this will be 1 over 5, so this will be here, let me write on here, so here you will get 6, and this will be 1 over 5, so it means this is 5, and the final answer t half-life, mean half-life in this case will be equal to 1.2 seconds, and your final answer will be equal to 1.2 seconds. So this is how you need to approach. So understanding of this one is very important. You need to understand meaning of each quantity. I hope this question makes sense. If these videos are helpful, they are helping you to improve your understanding of physics, please like and subscribe. And also if you have any questions, you can leave your questions in comments, then I will try to answer as soon as possible. And if you're looking for extra resources, join Patreon. On Patreon you will see more resources. See you next video.